The quiz won't pop up until tonight at midnight.
I meant the other homework.
According to this, it should have been up as of last night at midnight.
Oh, at midnight?
Okay, yeah, last night at midnight.
Let's say, I was working on it at 10.
And then the chapter, so chapter 12 remaining, so all chapter 12 homework should be open.
Okay.
And then chapter 13 homework starts opening tonight.
Is the intro to mastering 4th grade, or is that just?
No, that's just, that one's just there.
Okay.
That one's not for a grade.
I don't want to redo it.
Yeah, no, that one's not for a grade because I didn't know how many people had been in mastering. Yeah.
I was going to ask, how does this homework compare to that in statics? Because I noticed that there seem to be a lot more problems on this than in statics, but...
Well, let me open this one up and I'll show you. So in continuous motion, I want to do it as the student view. Student view, there.
Not really, but
Okay, so in the student view, what it's got in here is it will tell you that, like, the crossing the river, which is like a tutorial or an active example, it'll say it's 1 point for extra credit. So it's not part of the overall assignment. So that I am doing different than in statics. Statics, I just did anything that was in the homework was an assigned problem. But because I've got people everywhere with this one, what I opted to do was open up all the resources that I possibly could. So that, you know, if I didn't cover it in a lecture, you guys would have a chance to say, okay, I need help with this particular thing. And so what I've done is I've made it extra credit. Okay, I've made it extra credit. So there's some tutorial. Then it says, like, this is a fundamental problem from 1 point. Now, this one, 12-15, it's takes into a little bit more. It's a little bit more difficult. It's got a level of difficulty that was more on the 3 to 5 range. But it's a problem that I've picked because it's a problem that you'd see somewhere. You would totally see it somewhere out. Yeah.
I know that, like, for exams and stuff like that, you oftentimes will take problems straight from the homework and stuff like that.
Mm-hmm.
And I was curious, do you think that you'll take problems from the extra credit problems? Because I know that some people, like, they'll just do the normal
That's
problems.
necessary because of the usually busy schedule.
Yeah, and so like if you put like, do you get what I'm asking? Because like if you put
Yeah,
questions
and right
in
now I can't. I will tell you that we're probably right now. If I were making the test right over what I've done so far, you're going to have one that you're going to have to integrate over an acceleration. Whether that's a homework problem, a problem that we've done in class, or it's that type of problem has shown up in the extra credit. I haven't gone through the extra credits or the tutorials, so I can't even tell you what's in them. So is it likely, if I happen to pick one out of the tutorials, it's likely just a coincidence, okay?
I just don't want to be like really busy and then just do the normal problems and not do the extra credit, and then as it turns out, like 2 of the problems on the test were extra credit.
Right out of extra credit.
Yeah.
Well, if it happens, that's gonna be totally coincidental in this case. I'm not necessarily intending to go in there and look at it. So you've got the fundamental problems. Now remember, in Hibbler, you've got the workout for all the review problems in the back. You've got the answers to most of the problems, either be it a fundamental problem, a preliminary. Preliminary problems, they actually kind of give you partial steps. Fundamental problems, they give you partial steps. The actual problems, they just give you the answer. But they don't give you all the answers. If it's got an asterisk by it, it won't even give you that answer. So those are some of them.
Well, there are PDFs online of people walking through.
Some of them, yeah, because Hibbler's been around so long that you can probably find the answer to just about everything that's out there.
Like all the numbers are switched around, but it does show you the method of how to follow it.
Mhm.
Those are really useful.
Yeah, they are. They're somewhere out there. There's an actual Hibbler Solutions manual that you can purchase.
Yeah.
So that's where I've got this kind of stuff. So this one will tell you, if you go in, you can actually see what's for actual points for the homework and what's for extra credit. Okay? So hopefully that will help. It'll help keep things But and again, I've opened up all these resources because we've got people in various places and doing a whole bunch of stuff, and I'm trying to make it as open that are out there. So let me also get, so that one's due tomorrow. Under course materials and assignments, under the week 1, I've got materials for lectures. We're going to actually do some stuff on that today. Just to show you what I ended up doing so that you can actually see some things. And that's Monday's lecture. So Monday's lecture is on YouTube and it's already out there. And it is different than my ITV classes in that it shows the board and it shows me. It's kind of double screened. It's pretty cool. My ITV classes, it's not as nice. So Monday's lecture, and I'll try to get the lectures up immediately after class as I possibly can. But this week is a little tense. After class today, I've got another meeting, and then I'm still trying to get some stuff done. I'm working on a church history for our church, and I'm working on a couple other things. It's just like, and I got to get my column written. So, well, my column, actually, I know the topic, and I've already got a friend that's going to be on how to get rid of skunk smell. The actual chemistry behind how to get rid of skunk smell.
You know what I learned the other day? If you get sprayed by a skunk, or like if your dog gets sprayed by a skunk, if you wash them, it actually makes it worse.
It can, but the idea of the gal who she's a chemist, and she says she's got a recipe for washing with hydrogen peroxide and baking soda and a little bit of soap, and it's going to break the bond and the mercaptan, so it is not just an overpower. It's an actual chemical reaction with the mercaptan. All right, so let's go over this real quick. I want to see where I'm at. Where did I put my notes? Okay, all right. We're going to come back to that. I'm going to finish this one, and then we're going to start erratic motion. And I just didn't want to start this one yesterday because it was a little bit more complex.
So this is still on chapter 12.
Yeah, we're still in chapter 12. We'll be in chapter 12. We got to do projectile motion, and we got to do a few other things in chapter 12. But actually, this gets us, the problem I'm going to do right now is problem 1225. Let's see what we got. Okay, so 1225, we're going to account for the effects of atmospheric resistance from a free-falling body. So we're going to have an object that's falling.
Put the camera on the screen.
Okay, thank you. I'm trying to. Yeah, I got it. Each one is different.
Which problem is this? 12-what?
This is 12-25. So I've got an object that's falling, and if I did this in Gen Chem, I'm teaching Gen Chem in the morning, so I'm going to make that mistake all the time. So if I teach this in physics, we always say neglect air resistance, right? So now we're going to account for that air resistance. And if we do it, somebody's gone out and experimentally determined that it's going to look like this for the particular object that we have so that's going to be our equation for acceleration. So V is going to be in meters per second. Positive direction is downward. In this particular case, the positive direction is downward. We want to determine T is equal to 5 seconds. And then ultimately, which we probably aren't going to do, I'm just going to, but you may want to go in and look at it. You also want to find the velocity as T is approaching infinity. Okay? I'm only going to work at it from the 5 seconds. Because if you dive into this problem and you try to get the book solution, you're going to go, where did the heck did those constants come from? And that's why I picked this problem. One is it takes it from the next step of what we normally do in general physics to the step of, okay, now we're going to account for air resistance because we've been disregarding that all along. And now we're gonna actually bring it in, and we're gonna bring it forward. So remember that my acceleration is gonna be my dv dt. And I wanna find time, so I'm gonna rearrange this so that I'm gonna have my time as a separate integral. And I wanna bring it in there. And what it's also gonna do is I have my acceleration is a function of velocity. And that's gonna be really helpful for us. Okay, that's how I'm gonna determine what forms of the equations that I wanna work with. Is by go ahead and making sure that I've got this covered. So now I'm gonna do the integral of dt, because that's where we're gonna head first. And now I've got my dv 9.81, velocity 1 v squared 10 to the minus 4. All right, so here's trick number 1. Let's look at this 1 minus v squared 10 to the minus 4. One of the things you kind of want to notice is that my 10 to the minus 4 is actually 10 to the minus 2 squared. So now I'm going to have a 0.01 squared. So I can rewrite this term as 0.01v, all of that squared. And that's going to help me out in just a little bit. Because if I do that, we can do a couple of things. I can look at this, and let's look at its raw form first. Because this is where, because if I look at my integral tables, I can look at my integral table and I can look at this and I can have an a squared minus x squared. And that can give me a result. Okay. Or I can look at an integral that looks like, no, we don't want to do that one. So that gives me a result. Or I can do something else. Now this is the logic problem. When I look at my integral tables, x squared is not an ax squared. That's where the logic gets a little funky. It's not really. And what happens is you end up with the right form of the answer, but your constants are all off. Your constants are going to get all the way off, because what happens is this is going to, and I'm going to show you how this result looks. So if I look at my integral tables, I'm going to get this result, and it's going to look like this, and we're going to actually see, and if you look at the answer in the back of the book, you're going to go, okay, I've got the right form, but my constants are all off. And you'll see that in just a second as to why that is. So this, you have to be really careful when you're looking at your integral tables to verify, okay, and most of you know that you have to look and it'll have a caution that n can't equal 1. You know, I can do this integral that way as long as n is not equal to 1. Or I can do this integral this way as long as n is not negative. Or I can do the integral this way as long as this, or this. This one doesn't necessarily tell you you can't do the integral this way. And especially when you look at the answer, you're going to go, okay, but we do want to do this because of this. Because if I take 1 minus 0.01v squared, I can write this as 1 minus 0.01v times 1 minus plus 1 minus 0.1v. So I can factor it out. And the factoring is going to help me. And where you guys are going to end up probably struggling the most is not necessarily what the physics is going on here. Physics is easy. We got something that's falling, and I got to take into account air resistance. okay? And humid day, or if it's a dry day, my falling object's going to be a little bit off. And especially if I'm falling from a very great height, because ultimately I'm going to hit terminal velocity. And so the physics behind this problem is not hard. The solution to the problem is a little tougher, because then you got to figure out what on the heck am I going to do with this integral. So now I have an integral that looks like this. So I got dv 9.81, and now I have a 1 minus 0.01 v, 1 plus 0.01 v. Okay? So, then it becomes, how do I integrate that sucker? Integration by parts. No, this isn't integration by parts, this is integration by partial fractions. Now I looked at it and I went, okay, I know how to do this, but I can't remember what it's called. I can't remember how it's called. So, just to kind of refresh your memory if you haven't looked at it in a while, for our guys in the back that probably haven't looked at it in a while.
Our calculator does it for us.
Oh, your calculator does it for you?
Oh, yeah.
I had to do this on my DFQ final.
Yeah. But just to kind of people all over the place. So you got that. And then you remember that 1 has to equal A1 plus 0.1 V plus B 1 minus 0.1 V. So I get A plus B plus 0.01 V, A minus B, and A minus B has to equal 0, so A has got to equal B, and so A plus A is equal to 1, A is equal to 1/2, which is equal to B. So you can figure out your A's and your B's. So now what you end up with is, now I get 1 over 9.81, the integral of 1/2 d1 minus 0.01 v plus 1/2, or the integral 1/2 dv 1 plus 0.1 v. And now I can go to my integral table and life looks much better, because now I get ax plus b, and that's going to give me 1 over a natural log of ax plus b is the form. So the way I did it is I said, all right, I'm going to take my first integral. And this is where keeping your notes nice and neat is going to help you immensely, because I don't necessarily want to sit there and carry through everything all at once. So I'm going to do this integral, and that's going to give me 1/2, 1 over a minus 0.01, natural log of 1 minus 0.01 v. I'm going to have 1/2 the plus. Okay, I was going, what did I do? dv 1 plus 0.01 v is equal to 1/2 0.01 natural log of 1 plus 0.1 v. Started with, right? That's what we started with. So I'm going to have 1 over 9.81, and I have a 1/2, a 1 0.01. I have a minus the natural log of 1 minus 0.01 v plus a natural log of 1 plus 0.01 v. And if I get this part, here's my 1/2, and I get this, I'm going to end up with this part, natural log 1 plus 0(1)v divided by 1 plus 0(1)v. I got a minus somewhere. Yeah, on the top. On the top. No, the bottom one's minus. The bottom one's minus. That one's a plus. Because when I do the minus, if I go back and I look at my,
Oh, okay, never mind.
yeah,
I see.
this is LXY, just to kind of put it all on the same page so that we have it in our notes, right? Right?
That's what I was thinking, but I didn't see that minus in front.
Yeah, there's the minus right there. So that's why I get that. So that's the inside, and now my constant is going to be a lot different than, now if you go back and look at the other form, and that's why I said there was the logic error, look at the form. The form is identical. My form is identical, but my constant is all wrong. So that's why I said you got to kind of be careful when you're doing it, because this form looks really, really similar, but your constants are wrong. Yeah.
And so where exactly did it go wrong?
It going wrong here is that this is the integral from the integral table. So my a can be 1, my a can be any number, but my x can't be that. Because this x squared has a constant times the x. And that's where it goes wrong, in that this constant is going to be also affected by whatever constant that I have in front of the x. Which is why I got to go back to partial fractions. Yeah, because what happens is that then I totally disregard this constant all the way through down here, and when I do it, remember when we integrate, we're going to up there, but without it, this constant gets funky. And just as an FYI, what happens is, and as your book is working the problem, remember that this is all equal to t. Okay, that's all equal to t. So what they do is they take that 1 over 9.81 times t is now equal to 50 times the natural log of this 1 plus 0(1)v divided by 1 minus 0(1)v. And now you can start playing with all the other gory stuff to make it nice and put it in its exponents and whatever. But I wanted to get you to here so you could see, where did the heck did this number come from? That didn't quite match.
Would it have been possible to factor out a 10 to the second to get the AX?
You couldn't do that because you would have to factor out,
This is going to be the more straightforward way to do it than trying to factor that part out. You could have, I guess, but you're still,
Whatever works.
yeah. And it probably, and it might work. It might get you the right number in the front. I mean, and that's the thing about all of this, is there's usually going to be more than one solution and more than one way to do the problem. And that's one of those things that you got to kind of take into account. Okay. Now, here comes life. We've made life difficult. So we've gone from a constant acceleration, right, to that's a function of something, but the acceleration is a nice one function of something. And let's think, all of us got here today by doing a couple of things, right? So let's say we left we left our house, right? We backed up out of the driveway. I had to accelerate to get going to back up out of the driveway. So I had a driveway. I got to the road, right? And I accelerated to gain to a speed. I got to the stop. I had to decelerate to stop at the stoplight or the stop sign. Then I could finally get on Highway 60, and I go at a constant motion, right? I go at a constant velocity. And then I have to decelerate. The thing I just told you is we don't have one acceleration as a function of one thing. This relates to continuous motion. All right? But our motion isn't like that. All right? Our motion isn't like that. And so now we're going to call it erratic motion.
Is erratic spelled with an R or E? I thought it was
Yeah, it's a big capital E.
Okay.
Big capital E, erratic motion. And so that gets us over here to kind of look at. So if I look at, that's what I brought this back in here. So just to kind of remind folks, if you haven't looked at physics classroom in a while, you look at physics classroom in a while, you can get up here and it's got all kinds of things. And remember, we have shapes for graphs. So this was a momentum versus time graph, okay, or a velocity versus time graph. We've got a constant with a changing velocity. If I have a position versus, a P is position. So if I have a position versus time graph, and if it's a straight line, I'm traveling at a constant velocity. But if it's a curve, I have acceleration, right? If it's a curve, we have acceleration. So those first labs that we went back through, and we said, okay, think about what the graph is telling you. Think about what the graph is actually telling me. I'm getting my position versus time. I've got my position versus time, and I've got a curve. This has an acceleration. This one does not. This is traveling at a constant velocity. That one does not. So we can go back. Let's see if I can go back. I do like the smartboard on some cases. I really like the smartboard on some cases. So now I can do a velocity versus time graph. Okay, there's my velocity versus time graph. If I'm traveling on a straight line like this, I'm at a constant velocity and I have no acceleration. But my velocity versus time graph looks different than my position versus time graph. But if I have a changing velocity, this is a constant acceleration. All right? But now, if I have something like that, I'm traveling along at, 2 meters per second, and then all of a sudden I'm going to accelerate to pass somebody. Okay? I'm going to accelerate to pass somebody. But then you think about, wait a second here, this is good old general physics. We no longer have a constant acceleration. Our accelerations now can be a function of something. So I just kind of brought this one back out so that people could actually see the graphs. So then let's think about, let's go back here. I go to hyperphysics. I can have motion graphs that look differently. Okay? So this is a position versus time graph, but now I got a curve to it. My acceleration isn't necessarily a constant acceleration. I've got a velocity versus time graph. Now those are nice straight lines, so I have nice constant acceleration, right? If I've taken that graph to do those pieces. But now, and I can do my acceleration versus time graph, and I can see a constant acceleration. So we can actually start looking at how these pieces go in to actually play with it. So I gave you guys links to that. But now let's look at a two-stage rocket. Okay? there's a two-stage rocket. And if let's see if I can expand that out. My two-stage rocket, make it bigger. The first stage is going to go up a little differently than the second stage. This would be a case of erratic motion, and it just so happens in this particular case of the two-stage rocket, I have two different constant accelerations. But I could start to look at it in terms of the curves. And that's the real critical thing. I could start to look at it in terms of the curves, and we can actually play with those curves to give us that erratic motion. So you've got those pieces in there, and I'm going to go ahead and call up, because I want to show you. Now, are you guys using MathCAD at OSU? Okay, they want you to, but you don't use it. I'm going to use Excel instead of MathCAD because my guys don't have MathCAD.
What is?
I have MathCAD in Excel.
Yeah, I'm going to work in Excel.
What is MathCAD?
MathCAD is a it is an incredible math solution tool. You can put the integral in, and you can have it solve the integral for you.
So it's like a super duper calculator.
It's a super duper calculator.
And once you get all your formulas worked out, you don't have to change it.
Yeah. So if you're doing, like, let's say we're doing that air resistance, let's talk about what they're doing with SpaceX, right? What they're doing with SpaceX right now, or whichever one, my rocket now is going to have a certain coefficient of drag friction that I have. So if I'm going through the atmosphere and I want to know how it behaves, and I can put in that acceleration, just like what we just dealt with, and look at how it falls, I can put it all in MathCAD, and then I can make small changes in drag coefficient and know how it's going to affect things. So it's a
So it's like
slick.
simulation.
It'll do simulations. It'll do calculations. It's a slick tool. But so what we're gonna do? Make sure I've got my problems laid out. Okay, there's where I've got my problem laid out. So we're gonna actually look at those in just a second. So what we're gonna do now is we're gonna start bringing in erratic motion. So that's what we're gonna have, and what we're gonna see in the problems. And so I'm gonna bring up the book here. So what ends up happening is they're gonna start showing you a graph. So you're gonna have to interpret the graphs. All right, you're gonna have to interpret the graph. So what we've got here is I got a bicycle. So we're gonna get the bicycle for problem 11 here. Let's roll this in so you guys can see it. As my bicycle is traveling along a straight road where the velocity is described by the velocity versus position graph. So you're gonna have to watch what they're actually telling us in the information. And we wanna construct the acceleration versus position graph for this particular thing. So one of the things we know is that we're going to start, this is telling me I'm going to start at 0 velocity. I'm going to end up at 10 meters per second. It gives me, it's really nice, it actually gave me the slope. You'll find that a lot of the times the problem won't even give you the slope, and you got to figure it out, okay? So I've got it actually gives me the slope, and I'm going to reach 10 meters per second when I'm at 40 meters. So that's what it's gonna give us to work at. So
And it's asking for the acceleration what graph?
the acceleration versus position graph. S is going to be position. So it's asking us for our acceleration versus position graph. Now I don't know how mastering is going to have you guys put these in the homework, okay? Because all the homework is asking for these graphs. I just don't know how they're going to actually do it. So that's just something to.
Multiple choice, but at the very end.
Some of them-
Some of them are drawn.
Yeah, some of them are pick which one is the right graph. You know, that one. So this one we start out with that v is equal to 0.25 seconds. Then is equal to v dv ds. This is velocity. S is position in this case.
Oh, okay.
This is not seconds. Yeah, S is not seconds.
Yeah,
gonna be
I did a homework problem where it had something like that where it asked for like position.
Our book is using S to mean position.
And T is
and t is time. 0.25 s d 0.25 s ds. And so now I'm going to get, when I do this, I end up with 0.0625 s. And I need to do an acceleration versus position graph. So I can do a couple of things, right? I can do a couple of things. I can go ahead and say, all right, well, accelerate at A is 0 and S is 0. I know I've got my point there. My line, or my equation is telling me I've got a straight line, so a straight line. And I think it is asking, okay, it did 40 meters, because that was my graph that they gave me for 5 times my 40. And that's going to give me something that's 0.25 meters per second squared, just because that's what my units are in. So if I do this, I'm going to have my 2.5 and my position at 40. I got a nice, and I have a nice straight line.
So I can see divided by 0.25 s.
Mhm.
Where did the 1 over ds go? Where did the ds in the denominator go in that equation?
You're doing the derivative with respect to s.
Yeah, that makes sense.
Yeah, so all that stuff you've been doing mathematically is now being applied to the motion. So we're going to end up with graphical representations for a lot of things, okay? So we're going to end up with those graphical representations. So remember what your book is going to do. Your book is going to give you an S and T, and this is going to be a position versus time graph. I'm going to get V versus T. That's going to be velocity versus time. So just knowing what the book is going to look at. So if we start with a ds dt is equal to velocity, I'm going to get a ds is equal to velocity dt, where this is going to be, this V right here is going to be the slope of an S versus T graph. All right, that's going to give me the slope of an S versus T graph. Similarly, if I do a dv dt, which is going to give me an A, I'm going to get dv is equal to A dt. That becomes the slope of a V versus T graph. Now, again, these are making the assumption it's going to be a constant, all right? Because if I'm doing a slope, I'm going to get a straight line. But in erratic motion, it doesn't have to be a straight line. Okay? In erratic motion, it doesn't have to be a straight line. So if I look at dv a dt, or this becomes my change in velocity, I'm going to have the area under the curve is an AT graph. Okay, so my change in velocity, let me write it out, it's better. The change in velocity is going to equal the area under an AT graph. Similarly, my change in position on a VDT graph is going to equal the area under a VT graph. And then my average, if I go back and look at this, when doing that one, you're going to get this average velocity is the area under an AS graph. And then you can do something really weird. This actually is saying that acceleration equals velocity and that's the slope. Okay, the slope times a VS graph. So velocity equals the slope, okay, velocity times the slope of the VS graph. So you get weird stuff that you can start interpreting what the equations mean versus where we're at. Okay, so we're going to do a problem, and I'm going to use Excel instead of MathCAD. All right. So we're going to do problem 7. We have 2 rockets starting from rest. At a height h equals 0 for both. I'm going to actually give you exactly how it's written here because I added certain things into my notes. Two rockets start from rest at the same elevation. Rocket A accelerates vertically at 20 meters per second squared for 12 seconds, then maintains a constant speed. Rocket B accelerates at 15 meters per second until reaching a constant speed of 150 meters per second. Construct the acceleration versus time, the velocity versus time, and the position versus time graph for each rocket until it hits 20 seconds. And what's the distance between the 2 rockets at 20 seconds? If I were to give you this problem in physics class, I'd just say, what's the distance between the 2 rockets? If you were to get this problem in algebra class, it's what's the distance between 2 rockets. But now we want to actually look at the motion and describe the motion. So my first thing is I'm going to start with a height as h is equal to 0. Okay, where I'm starting. And we know that, so I've got rocket A, and it's accelerating at 20 meters per second squared. I'm going to say it's accelerating up for 12 seconds. And then it's going to maintain a constant speed. And then rocket B has an acceleration of 15 meters per second squared. Different information until it reaches a constant speed of 150 meters per second. We want to construct the AT, VT, and ST curves. Zero to 20 seconds. And then ultimately we want to know what is the distance. So here's one of the things that we have to worry about. I'm going to assume that both of them are traveling either left or right. The thing I'm making the assumption is I don't have to add in the acceleration due to gravity. That the motion that's being described is already incorporating gravity. It's not clearly stated in the problem, but I'm going to make that assumption. Alright, so that's the first thing. The second is I got to write the equations of motion for both rockets. So I'm going to start with rocket A. We know that the initial velocity is equal to 0. We know that we have a velocity of 20 meters per second squared times time. And I know that I have a position as 1/2
Did you say it was a second squared times time or equals time?
times time.
Okay.
Velocity is equal, this is velocity is equal to acceleration times time.
Okay, got it.
And I just put in the number. But this all is from 0 to 12 seconds. Okay, so that's motion that's happening from 0 to 12 seconds. Now, at 12 seconds, the velocity is going to equal my 20 times my 12 seconds, which is now going to be my constant that I have to worry about. And that ends up being, somebody calculate it. There's my calculator. I didn't calculate it in my notebook. 240. Which is equal to 240 meters per second. And S is going to equal my 20 times my 12 times time plus 1/2 acceleration times time squared. But they told us we're traveling at a constant velocity at that point, so I can get rid of that term. Okay, so that's rocket A. I didn't do rocket B in my notes. That's why I'm going to go ahead and come over and show you what I did in Excel. So this is this one. So what I ended up doing is for rocket A, okay, for rocket A, what I've done, and the reason I did it this way is to make it easy to show you how to do the graphs. There's other ways of playing. I hit a button and I didn't want a button. Okay, escape. There we go, good. All right, so there's my equation of motion for position until 12 seconds. Half of 20 is 10. So I've actually plugged that in there. There's my equation. And for you guys that haven't done it, when I put in an equation and I want to show the equation that I've put in and I don't just want it to do the calculation, you use the, I got enable editing. I have to use the little quotation mark, and then I can type in whatever my equation is that I want to do. So let's say that's the equation I want to put in. That way I can have you can show it. So I've put it in there, I have got into the different pieces, so now I can just do my plots. So here's my S versus T graph, there's my velocity graph, and there's the acceleration graph. So you can actually draw the various graphs in the system so you can actually see it. So that was rocket A. Then I did a workbook tab for rocket B, did the exact same thing to get the points in order to do the graph. Except now I had to do my position up to, I had to figure out what the time was for when it reached 150 meters per second. Since we were traveling at 15 meters per second, we knew that was going to be 10 seconds. And so I plugged that in, wrote my position versus time pieces, and then was able to plot the behavior of rocket B. And then ultimately, at that point, we want to know how far away they are. Well, my position on this one is that I'm 2,250 meters away. At rocket B, I'm 3,360 meters away. You take the difference, and if I take the difference, I'm 1,110 meters different between the two. So you can use Excel to really help you out. And we're about to use Excel to help me calculate the area under a curve. And I'm sure you could use Google Doc or Google Sheets just the same, but I just happen to use Excel. And if you have a really nice graphing calculator or MathCAD or a variety of other tools, and you all know that the killer app for the PC was the spreadsheet.
No, I did not know that.
Yeah, that's why a personal computer, because the spreadsheet, not the word processor.
What about Symbol Lab? Can Symbol Lab do stuff like this?
I don't know about Symbol Lab. I have no idea.
Yes, symbol lab. Well, I don't know if you could find the area under a curve, yes.
I honestly don't know.
Just most graphing calculator, you can graph the.
Yeah.
Man, y'all know so much more than me.
I got a lot of resources.
Okay, so we're gonna do problem. Let me see where. Yeah. Okay. Yeah. This is the one. Problem 46. I picked this one because it was like, okay.
That's 1246?
1246. Yep. 1246.
Be scary if it was 13.
I gotta switch. No, we haven't gotten that far yet. Okay. So this is 1246. So we're given an acceleration versus position graph. And we've got a rocket moving along a straight track, and it's been experimentally determined. Okay? If the rocket starts at S is equal to 0 when V is equal to 0, determine the speed as it hits 75 feet and 125 feet respectively. Rule with n equal 100 to evaluate the velocity at S is equal to 125 feet. Okay? So we're going to use Simpson's rule in order to do that. So that's our lovely question. You want to look at, we've got to write down a few things. One is, if I'm looking at my graph, it gives me at 100, and I start out at S and straight, and then I have a curve, and that curve was A is equal to 5 plus 6 square root of S minus 10 to the 5/3. And this was 5. And this is an acceleration, and we're in feet per second squared. And we're in a position and we're at feet. So the first thing that we want to do is we want to determine, I'm going to go S at 75 feet. My A is equal to 5 feet per second squared. I'm going to use V final squared is equal to V initial squared plus 2A times my change in position. We were told that V naught was equal to 0, so I can get rid of that. V final squared is going to be 2 times 5 times my change in position, which was 75, which is going to give me 750 feet squared seconds squared. And it gives me V final is equal to the square root of 750, which is equal to 27.4 feet per second. The key thing here is the next one we want to find at 100 feet. Because I'm going to have erratic motion starting at 100 feet. So I'm going to need to know that 100 feet mark, because that's still going to have my acceleration as 5 feet per second squared. My V final squared is going to be 2 times 5 times 100, which is going to give me 1,000, and it gives me V final is equal to 31.6 feet per second squared, or feet per second.
Can you scroll down, please?
Wouldn't it be 10?
Take your square root of 1,000. I did the same thing. It's okay.
What were you trying to do, Kristen?
The square root of 100 is 10.
Oh, yeah.
And when you look at 1,000, you immediately your brain immediately goes to the 10. I mean, it just immediately does because you're so used to it.
Try to solve it in your head so you don't have to get a calculator out.
Right? Exactly. I did the exact same thing, and I went, "Wait a second, I can't do that."
Isn't that weird how 100 is a nice like rounded number, like 10? Like, oh, it makes perfect sense. And then once you get to 1,000, it's like 31.6.
Yeah, it's just the way it is. All right, so let's remember Simpson's rule. Everybody remembers Simpson's rule off the top of their head, right?
Sure.
What's Simpson's rule?
Okay.
That's what I remember about Simpson's rule.
Okay, so remember what happens is that you can determine the area under the curve by taking teeny tiny little slices, right?
I do remember that.
Okay, you can take that under the curve. And what happens is that my area is going to equal A minus B divided by the number n, okay? A minus B divided by the number n, and then you end up with these things like y naught plus 4, and you end up with this pieces that you plug through. And in fact, it works out with like it's like y naught plus 4y1 plus 2y2, and it goes through this sequence that you can do it. But A and B are your endpoints in the problem. And essentially what you're doing is this. You're taking your 1/2 V final squared minus V initial squared is equal to my integral of from 31.6 V, because that's my starting spot, right? That's my starting spot. And that comes from this V dV. And that's going to equal 100 to 125 of my acceleration ds. And my acceleration that I'm worried about is my 5 plus 6 times the square root of s minus 10, 5/3 ds. Now, the part that we're going to have to use Simpson's rule for is this creepy part over here. Because this part's easy. because I'm gonna have the first integral from 100 to 125 is 5ds plus 6 times the integral of the square root of s minus 10 to the 5/3 ds from 100 to 120 or 125. My books are in the way, so I can't push that up there. There we go. And that's 5/3, sorry. So everybody got that part? Oh gosh, did I not put it up here? Oh shoot. This is a different one. That was just erratic motion. I'll have to put it up there for you. I didn't get it uploaded on the Blackboard. I didn't get it uploaded. That's a bummer. Because I got the Rocket A and Rocket B one, and I've got the other one that's got the Simpsons rule in it. I'll have to bring it. I'll upload it and show you guys tomorrow. Because when you do it, it actually totals up and it gives you a really nice total, and gives you the total is 308. So
That's not actually two part of a equation to.
it's not actually a two-part of an equation to integrate, but they went ahead and wanted you to use Simpson's rule. They specifically did it, and I've got the Excel workbook with it in there, so I will get it for you guys. See, I told you it's been a crazy week. It's this right here. Hang on, switch it back. Is that you can integrate under the curve using this sequence. Yeah, that's Simpson's rule. And you can integrate it, and what it ends up is, this ends up being, you end up getting a different, you end up getting like 202 once you finally get the numbers all put into place. But that's how you set that one up. Okay, I've got to make myself a note. Find my workbook. Okay, so I'm gonna get that one in there. All right. Okay. I'm gonna do one more, and then we will call it good, and we'll start projectile motion. Yeah. We're going to do this one, 54. We've got a VT graph, and it's going up as 0.6 t squared. And then we have it coming straight down. And we want to determine the average speed and the distance traveled for the 15-second time interval. So we're going to end up looking at that graph. So I'm going to end up with a graph that looks like this, or start out with a graph that looks like this. And this is one that they don't give you all the information from the graph. You're going to have to get some of that information. So I get V is equal to 0.6 t squared, and this is the v, and this is the s. And this part and that part, 5 and 15. So from 0.6 t squared, I want v at t is equal to 5, because I'm going to need it at some point, and that turns out to be 15. And we can get that information straight from the graph.
So is the x-axis supposed to be time?
This is position. Remember, s is position, not seconds.
It's just weird seeing the equation in terms of time and the graph in terms of
Yeah.
Gianna,
No, it is time. I'm sorry. That one is time. That one is time in seconds. Sorry.
what I was gonna say is, you know how like in chemistry, like everybody has like an agreed upon symbol for like for the elements, for example.
Uh-huh.
Like everybody agrees hydrogen is H,
Yeah.
right? How come like in physics we don't have an agreed upon symbol for speed
Because
or
different
position or
symbols
anything?
are used in different types of engineering to make it
Yeah.
simple.
It's your common. Well, if you think.
It's kind of like a language,
Yeah.
It's
Well, that's why we're using S, because S could be X, Y, or Z, or R. Yeah. Oh yeah, Q. Rho is my favorite. Rho is used for all kinds of stuff.
In geotech, he used little q for, what was it? Q is the flow rate, and then he also had q as the.
Well, see, Q is heat. See, Q is heat.
Oh, Q is flow rate.
Q is heat, man.
It has many meanings.
Yeah, so we get it.
I
Yeah.
feel like we have to make like an expanded alphabet with like 150 letters to make up for.
Well, you get several things. All right, so 5 to t is equal to 15, right? We're going to have v is equal to v naught plus at. But we're going to do it a little differently. So I'm going to start with a is equal to, or find a, because we're going to end up finding a in a variety of things. So we get a is equal to dv dt. So that becomes really nice because that becomes d 0.6 t squared dt, which ends up becoming 1.2 t. And that's for a 0 to t is equal to 5. And then at 5, we get v is equal to v naught plus at. And I can use this slope up here. The slope is minus 15 divided by 10 is going to be minus 1.5 t. So if I go beyond this, my acceleration ends up being minus 1.5 t for that second half. Then I can do the position. So if I do position 0 to t for 0.6 t squared dt, but this will go for my 0 to 5 seconds. So 6 divided by 3 t cubed, evaluated from 0 to 5, right? And so just at 5 seconds, S is going to equal 0.25 cubed equals 25 meters, because I'm probably going to need that. And now when I go from 5 to t to 15 seconds, That'll help. This is where things get funky. So I'm going to do the change in velocity over the change in time. I'm going to have v minus 15, t minus 5, and that's going to equal my negative 1.5. And that comes from my graph, which was 15 minus 15 over 10. This will give me v minus 15 equals negative 1.5 t minus 5. This ends up being minus 1.5 t minus plus 7.5 v minus 15. But so I'm going to get rid of this, so I end up with 15 minus v is equal to 1.5. And take my 7.5 over here, I get 22.5 minus v is equal to 1.5 t. V ends up being 22.5 minus 1.5 t. And the reason I want to do that is because I want to take my S starting at 25 meters to S, ds is equal my, from 5 seconds to any time t after that, 22.5 minus 1.5 t dt. Luckily for us, that's an easy integral to integrate. So this side becomes S minus 25. And this becomes 22.5 t minus 1.5 divided by 2t squared, evaluated from 5 to t. So I'm going to end up getting 22.5 t minus 22.5 times 5 minus 1.5 t squared plus 1.525 squared. And that ends up getting you something that looks like S25 minus 22.5 times 5 plus 25, 1.5 divided by 2 plus 22.5 t minus 1.52 t squared. And then if you plug in for t is equal to 15, S equals 100 meters. All of that to get 100 meters. And then V average becomes really easy because then you take 100 meters divided by 15 seconds and it gives you 6.67 meters per second. Which is one of the answers that you needed.
So, Okay, I forgot. What's the difference between instantaneous velocity and average velocity?
Average velocity takes my change in velocity over time. Instantaneous velocity is that I'm going to an incrementally small time. So if I have a velocity versus time curve, my instantaneous velocity would be whatever that velocity is at that moment.
Gotcha.
Change in over change in time.
It's like taking, looking at your speedometer while you're driving versus how far you're driven and how long it takes.
Exactly. Exactly. Okay, so we're going to start projectile motion, then erratic motion. Get that tomorrow, see how far we can get, and go from there.
That's
Quiz is open tomorrow?
Quiz should open tomorrow, yeah.
When will it close?
Oh, I don't remember. We'll have to
Is
just
it-
look at it.
We still only get one try on each problem, right, on the quiz?
On the quizzes, yeah.
Okay. On the homework, we get 6 tries.
You get however many it is. I didn't, because I think it's,
I figured,
Didn't-
well, since we have 6 tries on the homework, maybe we have 2 tries on the quizzes, like.
No.
no.
You're not that like
Yeah, you should definitely
Yeah.
change that to 2 tries.
No.
That would be kind
That would be like proportional.
that.